which goes like this. So quick graph. Stay where you are.
All right, so
the high point
is
37 inches.
What's the low point?
13 inches.
Okay.
Graph, and I did it in pencil first because we screwed up like the first 3 of them. So let's make a crisscross. There's our crisscross, and our high point was at 37, and our low point was at 13, so that makes our dotted line at 25. Okay. And we had a low point at 1 second, and a low point at 3 seconds, and a high point at 2 seconds, and another high point at 4 seconds, which makes our period 2 seconds? Mm-hmm. 2 seconds, okay. And now we make our voluptuous curve. Ta-da!
So here's our amplitude. And it is, what is it?
12.
12. Oh, upside down. My bad. Okay, not 21, 12. And so that's our amplitude. And then our period is, we'll measure from this low point to this low point. And that's 2 seconds. So that's our period. And we forgot to mention that the vertical displacement is at 25. That's the average of our high and low points. Okay, so that makes our equation. Hold on. Okay, 25, which is the vertical displacement, plus 12, the amplitude, cosine. And then to get the b value, you do 2 pi divided by 2, which is our period. So you get pi, and then x, because there's no phase displacement.
You're so smart, Erin.
Our first word problem is how high was Aaron at 1.5 seconds? So what we did was we went over to 1.5 seconds on the graph and DD'd up to the line and then DD'd over to the inches side and found that it was 19 inches. The answer to our first word problem is 19 inches. Our second word problem was how high will Aaron be at 2 minutes? To solve that, we converted minutes into seconds by multiplying 2 minutes by 60. We got 120 seconds. And then we plugged that into our equation. So it was y equals 25 plus 12 cosine of pi times 120. And after we plugged that into our calc, we got y equals 36.5 inches. So at 2 minutes, she'll be at 36.5 inches off the ground. Our third and final word problem was when will Aaron be a foot off the ground? If we look at our graph, you'll see that the lowest point she ever gets to is 13 inches, which means she will never be a foot off the ground.
Unless it breaks.
Unless it breaks.
Okay. So, sinusoidal functions are important in cases like this because the guy who designed that lovely teeter-totter over there would have to use a sinusoidal function to make sure that that thing never hit the ground or went too high so that it broke. Okay. I'll poop now. It's uneven. No, I'm starting over.
All right.
Maybe we should can we do like a thingy? Like a zigzaggy thing?
Okay.
37. And that will be our high point. Wait, are we starting at 0? Oh my god, that's a really big thing.
What?
Oh, squish it.
Squish it.
No,
no,
grab.
that's my homework book.
No.
Okay.
Where'd it go? I don't know.
Okay.
And
Okay.
Put an X in it.
Oh well. Oh well. Okay. Are we still going?
yep.
Okay. So now we solved the problem.
Like, what are we doing? I don't know.
What are we doing?
I don't know. Let's all fall off.